Hi, I'm Noga, I'm from the Weizmann Institute, and this talk is based on joint work with Guy Rothblum. The talk is going to be about proof systems, and we start with some brief motivation. So assume we have some weak client who wants to run an expensive computation, but due to lack of resources cannot perform it by itself. So it uses some untrusted cloud or server to do the computation for it. This task is called delegating computation, and we model the computation by a language L and an input X, such that the client wants to know if X belongs to L, and the server always tries to convince it that this is indeed the case. We call the client the verifier, and we denote it by V, and we call the server the prover, and we denote it by P. And these two parties interact, and at the end of the interaction, the verifier decides whether he accepts or rejects. Completeness means that for any X in L, the probability over the verifier's randomness that he accepts is equal to 1. Soundness means that if X is not in L, then for any cheating prover strategy P star, the probability that the verifier accepts is less than half. And this half can be made smaller using repetitions. Okay, here comes the difference between an interactive proof and an interactive argument. So in interactive proof, soundness is guaranteed against any unbounded cheating prover P star. Whereas in an interactive argument, soundness is only guaranteed against polynomial time cheating provers. Each protocol has 4 complexity measures. The first is the communication complexity, which means what is the overall number of bits exchanged during the interaction. The second is the round complexity, how many rounds of communication did the protocol have. Notice that each round is 2 messages. We have the verification time, which is the running time of V, and we have P time, which is the honest prover's running time. Now, another requirement that each protocol can satisfy is called double efficiency, and we denote it by DE. And we only define it for languages in P because these are the languages that we're going to deal with today. So the first condition is that the verifier should be super efficient. It should run in time which is almost linear in the size of the computation. And the second condition is that the prover should be relatively efficient. It should run in time which is proportional to the size of the computation, which in our case means that it should be polynomial. So the question that we ask today is as follows. What cryptographic assumptions are needed for building arguments for languages in P, where our focus is on constant round arguments that have almost linear communication complexity, almost linear verification time, and a polynomial time prover? Killian showed that if we assume CRH, then we can achieve what we wanted. So what is a CRH? Collision-resistant hashing. These are shrinking functions that are hard to find collisions for. Namely, if an adversary gets a function h sampled at random from a CRH collection, then it is supposed to be hard for him to efficiently find x and x prime such that h of x is equal to h of x prime. And Killian showed in 92 that if we assume the existence of CRH, then we can get what we wanted. And even something better, actually, we can get sublinear communication. Killian works for P, and it even extends for NP. So Killian is great, and it achieves what we wanted, but a central theme in the theoretical studies of crypto is asking ourselves what are the minimal assumptions required for doing something. And in particular, we often ask ourselves, is it possible to replace CRH with one-way functions? So we're not going to define one-way functions today, and we're not going to use them directly. Rather, we're going to use some equivalence between their existence and the existence of another object called YOF. So YOF stands for Universal One-Way Hash Functions, and we're going to define them later, but for now we just need to remember that if one-way functions exist, then also YOFs exist. Now we're ready to present the main result. We call it flat GKR, and this name will become clear soon. So let me just define what does log space uniform depth D size poly means. So we have two models of computation, right? We have Turing machines and we have Boolean circuits. And today we focus on Boolean circuits. They have two parameters, each circuit. They have the depth that we denote by D. D is a function of n, where n is the input length. And they have the size, and since we only consider languages in P today, the size is always going to be polynomial. Now, what does it mean for a Boolean circuit to be log space uniform? It means that there exists a log space Turing machine that can output its description only using logarithmic space. Okay, so the theorem goes as follows. Assume one-way functions exist. Then, for any sigma between 0 and 1, every language L computable in log space uniform depth D size poly has a constant round, doubly efficient interactive argument with the following parameters. So the communication complexity is D times some small polynomial overhead, n to the sigma. And the verification time is D plus n times this small polynomial overhead. The round complexity is 1 over sigma cubed, and the prover runs in polynomial time. Now, notice the trade-off between the round complexity and the communication complexity and verification time. We can take sigma to be arbitrarily small and to bring down this polynomial overhead, but this will cost us in round complexity and vice versa. Now, an immediate corollary is if we plug in the best D, if we take D to be linear, a linear depth circuit, then we get that the communication complexity and the verification time are both n to the 1 plus sigma. So we start by comparing this result to known protocols. Okay, so the first column is just flat GKR from the previous slide. I copied it here as is. And the first protocol that we want to compare with the flat GKR is, okay, as expected, GKR. So GKR is an interactive proof. It's a work of Goldwasser, Kala, and Rothblum from 2008. And GKR achieves the following parameters. So first, it also works on families of log space uniform Boolean circuits with depth D and polynomial size. And the communication complexity and verification time are even slightly better than flat GKR. Why? Because this O tilde hides some polylogarithmic factors. So the overhead here is better. It's polylog versus small polynomial. And another aspect where GKR is better is the assumption. Okay, we said that GKR is an interactive proof. Flat GKR is only an interactive argument. So in interactive proof, we assume nothing. But on the other hand, we pay with round complexity. Okay, the number of rounds in GKR grows linearly or even bigger than linearly with the depth of the computation. It is O tilde of D. Whereas in our case, it is just 1 over sigma cubed, a constant. And the second protocol to compare with our result is Killian's protocol that we discussed earlier. So Killian assumes something stronger. He assumes CRH, but he also gets better parameters. So in Kilian, the communication complexity and the verification time, all of the complexity measures are independent of the depth of the computation. Okay? And also, the round complexity is some global constant, 2. It only has 4 messages. And the last result that I want to mention is by Reingold, Rothblum, and Rothblum from 2016. They construct constant round interactive proofs for bounded space computations, but since they use the model of Turing machines, the result is incomparable both to GKR and to flat GKR. So as the name flat GKR hints, our starting point is going to be the GKR interactive proof. So we start with some overview about how this proof system works. So we have a Boolean circuit. Each red circle is a gate and each black line is a wire. And we number the layers of the circuit from top to bottom. So we call the first layer W1, this is the output layer, and the last layer WD, since we have D layers. So this is simply X, the input. Notice that the computation goes bottom up, although we number them from top to bottom. And how does the computation with the Boolean circuit work? So we plug here the input, then we can compute each gate. We can think of these gates as AND, OR, and NOT gates. So we compute each of the gates. This propagates up until we have computed the output bit. So the circuit satisfies that if X belongs to L, then here it should be a 1, and if X is not in L, then the output is a 0. So GKR unwinds the circuit computation layer by layer from top to bottom. Notice that once each of the gates of the circuit is computed, we can simply view each of the computed layers as some Boolean string, and we can apply some encoding on this string. So we denote the encoding by ECC, error correcting code, and we use the word claim to describe a pair, RI-VI, such that the claim RI-VI is a correct claim about WI if the encoding of WI at coordinate RI is equal to the value VI. And the GKR consistency subprotocol reduces a claim RI-VI about the encoding of advanced step I into a claim RI plus 1, VI plus 1, a claim about the encoding of an earlier step I plus 1. And a very important point is that this consistency subprotocol can be implemented in a constant number of rounds. The soundness guarantee of the consistency subprotocol is as follows. If we started with a false claim RI-VI about layer I, then with high probability, the output claim RI plus 1, VI plus 1 is also going to be a false claim. Now notice that the prover always starts with a false claim, right? Because the output bit, if computed correctly, is actually 0. So he must lie and claim that the output bit is 1. But then he has a false claim about the first layer, which with high probability is going to be reduced to a false claim about the second layer, and so on until he reaches some claim about the last layer. But a claim about the input is something that the verifier can just check by itself, right? Because he has the input. So the verifier checks the last claim, RDVD, and see that it is false and rejects. And the only thing that bothers us is that these consistency subprotocols work iteratively. Okay, we have to execute them one after the other because the output claim of layer I-1 is the input claim for layer I, and so on and so on. So we cannot actually perform these consistency subprotocols in parallel because we don't have the input claim and we have nothing to do with the output claim. And here comes the flat GKR idea, to commit and then to parallelize. We want to commit to the values of each of these encodings of the computer layer such that we will get somehow the input claim for layer I, let's say, and that we will be able to verify the claim about the next layer that the consistency subprotocol is going to output. So flat GKR is going to start with the prover committing to the encodings of each of the circuit's computed layers and sending over these commitments to the verifier. So we denote these commitments by Y1 up to YD. And we can already notice that we have to make sure that these commitments are succinct, okay? Because we're going to pay on them with communication complexity and we don't want to pay too much. So the prover sends some short commitments to each of these encodings, and using these commitments, we are able to parallelize the consistency checks of GKR. So for any circuit layer I in parallel, we want to catch the following situation. The cheating prover P star sends a false commitment YI, but a correct commitment YI plus 1. Okay, first let's get convinced that this thing happens. So we claim that the verifier can verify Y1 and YD by itself. Why? Because he knows the strings that the prover commits to in both cases. Here it is just going to be 1, the alleged output bit, and here it is the input. And this means that Y1 must be false, because a correct Y1 means that the output is 0, which is the opposite of what the prover is trying to prove. And it also means that YD must be correct. And if so, then by a hybrid argument, there must exist some layer I when the prover switches from false to correct. But what can we do in this layer where the prover sends a false YI and a correct YI plus 1? So assume for a moment that we have some claim about layer I. This means that we can use GKR consistency subprotocol like we wanted, and to reduce this claim into a claim about the next layer that we denote by RV. Then the prover can locally open the commitment YI plus 1 at index R. Okay, what does locally openable mean? It means that the prover can convince us of the value of the string being committed to at a specific coordinate without sending over the entire string being committed to. Okay, this is important for us because we want to save in communication complexity. So the verifier asks from the prover to open YI plus 1 at R, and then he compares the results with V. And notice the very important point that we only need binding for a correct YI plus 1. So we have some relaxed binding property that this commitment scheme needs to satisfy when comparing to the standard binding property. And we also want to mention that the commitment scheme does not necessarily satisfy hiding, unlike the standard commitment scheme, which should be binding and hiding. Now we take a short detour, we describe the commitment scheme and how it is implemented. So what properties do we need it to satisfy? The first is based on one-way functions. The second is to be succinct in order to save in communication complexity. The third is that it's going to be locally openable, which we just discussed. And the main point is the security property. We call it second pre-image security. And this means that we only require binding for a correct commitment. So now we finally define a YOF, which is a primitive that we are going to use in order to instantiate the commitment scheme. So as we said, YOFs are equivalent to one-way functions, and let's see what is a YOF. So it has efficient sampling, computation, and short description. These three hold with respect to one-way functions and CRH as well. And its security property, second pre-image resistance, goes as follows. The sender declares some string X, then it receives some YOF H, and it needs to find X prime such that H of X is equal to H of X prime. And the success probability in the security game should be negligible. And perhaps, as you guessed, the commitment scheme is going to be implemented using a YOF tree. Okay, so this is a standard Merkle tree when each of the functions is going to be sampled from a YOF family. And indeed, this YOF tree satisfies all of the properties that we wanted. Getting back to flattening GKR, let's exactly see how do we use the commitment scheme in layer I+1. So the prover implicitly declares the value encoding of layer I+1. And this value is something which is determined before the protocol even begins, right? It's just the value of the circuit when computed on X after we apply some encoding on it. So the prover implicitly declares this string. Then the correct yi+1 is well defined, and the security property applies. The security property in this case means that if yi+1 is the correct commitment to layer I+1, then the commitment is binding, which means that the prover cannot open index R to anything but the actual value of the encoding of wi+1 at coordinate R. Now recall that we assume that we have some claim about layer I, and we reduce this claim using the consistency subprotocol to a claim about the next layer and opened the commitment for it. But how can we get this claim about layer I? And in particular, we need to use the fact that we know that this yi is false. So we want to translate the false commitment yi to a false claim about layer I. And this is the main technical tool of this work. We call it the translation protocol. It is an interactive proof, actually not an argument, that translates a commitment to a claim about the encoding of the string committed to. And it runs in a constant number of rounds. So this proof uses the structure of the commitment scheme. It uses the fact that we use a hash tree, but it does not use the security property of the hash functions that we use. Namely, it does not use the security of the YOFs. And it works for any unbounded cheating prover. Now we state the completeness and soundness of the translation protocol. So as we said, its goal is to verify that y is equal to the hash root of w. Its input is divided into two. It has the explicit input, which is the commitment y and the function h, not necessarily a YOF. And its holographic input is w. What is a holographic input? It means that the verifier cannot access it. Instead, it outputs a claim RV about its encoding, such that if y is the correct root, then this claim is correct, and otherwise, with high probability, either the verifier rejects or this claim is false. Okay, so that's it. We saw that one-way functions imply succinct, locally openable commitments with second preempt security, and that these in turn imply constant round arguments for languages in P. Now, two open questions are, based only on one-way functions, can we lose the dependence on D and create arguments for P or maybe even for NP, like Killian's arguments? And the second question is, can we create some general transformation for any IP? Like we took GKR and flattened it, maybe we can generalize this idea somehow and take any interactive proof with a super constant number of rounds and flatten it to be an interactive argument with a constant number of rounds. Thank you very much.